to talk about this topic, which honestly I feel like there's people in this room who know actually a lot more about aspects of this than I do. Hopefully I'll kind of convey some, maybe a different take on things, or sort of thinking about like the implications of different pieces of this. So hopefully each of you will find something interesting, and hopefully you won't just think I don't know what I'm talking about. So as just a tiny bit of background on me, and sort of as context for like kind of the framing that I bring to this stuff, is so I got my PhD here in statistics, but for almost 18 years, so I've been at Hopkins in the School of Public Health, and straddle sort of mental health and biostatistics. And so a lot of my work is sort of at the interface really of how do we implement methods in practice, and sort of motivated by real world challenges and such. And you'll see this was is in that spirit. So I want to acknowledge, so first Carly Lupton-Brantner's name's in bold because this is mostly her dissertation. She actually has her defense a week from yesterday. So she's heading off to Duke. And then also Leon DeStefano's another PhD student. And some great collaborators on this work, and funders, including NIMH and PCORI, which I might say a tiny bit more about, but really helpful for getting the EHR data especially. And we use trials from this resource called Fifthly. Okay, so I'm gonna motivate sort of some of this from, there's this real push in many fields for kind of what works for whom, personalized medicine, treatment effect heterogeneity, et cetera. And I see this in education research, and I see this in mental health research. And in fact, the National Institute of Mental Health, in their request for proposals for randomized trials, basically requires people to do moderation analysis and sort of look at treatment effect heterogeneity. It also requires mediation analysis, which is a whole different talk. But this project was in part motivated by helping think through, okay, it's easy to say to do moderation, what does that really look like, and how feasible really is it? But again, sort of the goal is this ultimate goal of can we determine how to best assign treatment, sort of who really is going to benefit from one treatment or another. So this would be great. But the problem that a lot of people now are trying to solve is that this is quite challenging, especially with individual data sources. So I'm kind of don't need to give the basics on all of this for this casual causal group. But randomized trials are wonderful because they provide unbiased treatment effect estimates, and people often will look at subgroup effects. They'll say, old and young, or, this characteristic or that characteristic. But they are usually powered just barely for main effects. They enroll the minimum number of people to have statistical power for an overall main effect. And there's a rule of thumb, total ad hoc, but a little rule of thumb, that to detect treatment effect heterogeneity, or whether effects vary across groups, you need about 4 times the sample size for even just 2 subgroups, like old and young. We need 4 times the sample to know whether effects actually differ for old and young people. So it's unrealistic that a given randomized trial is really going to have statistical power for that. And I was telling Luke earlier, just as a little anecdote from education research, I do work in generalizability of randomized trials, and a very famous methodologist in that world has said, well, I don't think this generalizability, external validity stuff matters because we have no evidence that treatment effects vary across schools or students or whatever. And it's well, that's probably partly because we're not powered to detect that. So, this matters for kind of decision-making and such. Okay, so that's yeah, Luke, great.
I remembered a critical detail of the Gelman anecdote where Andy Gelman stood up and told everyone that they were wasting their time looking for treatment variation, because his argument further is that interaction effects are probably going to be on the order of half your main effects, which would then cause you to go up to 16 times. 16.
Oh, I like that. Yeah.
So you truly do.
Yeah. And you'll see at the end of this talk, it's going to be my own personal, what am I doing here? And is there any point to any of this? But, which is related to that. Okay. So trials are great for what they are, but they're small. Non-experimental studies potentially have very large sample size, and Gary and Kosuke and I have written papers about kind of trade-offs in different study designs. They might reflect more kind of real-world use or representative populations, but of course they suffer from confounding. So basically the idea is to try to combine these different data sources to use the unbiasedness of the trials and the representativeness and large size of the non-experimental studies to learn about effect heterogeneity. So in my world, I have to write grants to support my work. So I wrote these grants like now 4 or so years ago. And in the time between submitting the grant and getting the funding and starting on the work, this area just exploded. And people in this room work in this area. And like every month, it feels like there's a new paper on data fusion, data integration. I don't know, there's like also 18,000 names for it. Like hybrid designs, IPD meta-analysis, again, and they kind of all have the same spirit of trying to combine data to do better. So our work is sort of twofold, and again, it's sort of in the spirit of much of what I've done, is sort of helping think through these different approaches and when different approaches make sense. So far, we're mostly focusing on some machine learning approaches and some Bayesian methods to combine multiple trials. I sort of got you all here by promising combining trials and non-experimental, but as we see to the end, I'll highlight why we're not quite there yet, because it's like just too challenging. And essentially, partly also, for now, I'm going to focus, for this talk today, I'll focus mostly on the machine learning methods. My collaborator, Huanyi Hong at Duke, is doing more of the sort of Bayesian approach. So for now, I'll focus more on the machine learning. And this is really, again, also a crazy growing area of like new papers all the time about this method and that method to examine treatment effect heterogeneity. Okay, makes sense so far? All right, so this work for us is motivated by this application of depression, treatment for major depressive disorder, in particular, to medications. So duloxetine and vortioxetine are the two medications we will compare for individuals with major depressive disorder. And so this is where I'll show you the data in a second, but are combining some trials from Vivli with Duke and Hopkins EHR data. Vortioxetine, just as context, actually, on the next slide, was sort of the newer drug that came on the market, and sort of, so most of the interest, really, in a sense, is vortioxetine more effective than duloxetine, which is more of the sort of standard approach. So just as a little bit of context for major depressive disorder, about 30 to 40% of people with major depressive disorder go into remission after sort of standard therapies. The first-line treatments are things you might have heard about, like on TV, Prozac, Zoloft, sort of standard. Those are known as SSRIs. Duloxetine and vortioxetine are sort of slightly newer medications that are meant for people who maybe don't respond to the first-line SSRIs. There's some side effects. And in general, what's interesting to me, and I'm sort of still grappling with some of this, and we actually had a little exchange with one of the data providers. The trials, interestingly, are usually 3-armed trials. So placebo, duloxetine, vortioxetine. But the comparisons that get released and presented are each drug compared to placebo, not drug to drug. And so actually, and they kind of complained to us when we were presenting results comparing duloxetine to vortioxetine. And we're like, well, it's a valid comparison in this trial. Like, there's some generalizability concerns that I won't talk about. But and interestingly, like for regulatory purposes, it's like, can vortioxetine be approved? I.e., is it better than placebo? But we're using it for this duloxetine-vortioxetine comparison. And that's partly, honestly, like in the EHR, I mean, that's the more clinical comparative effectiveness kind of question, and it's not like the EHR data has placebo in it. Okay, so more information on the trial data. So we're gonna have data from these 4 randomized trials that we got from this Vivli data source. So Vivli is a clearinghouse, basically, where they collect trials from some pharmaceutical partner companies who allow for their data to be used for research purposes. You have to like do it through their system, et cetera. anyway, so that's where they come from. So each of the trials has about 400, 500, 600 people in it. Eligibility criteria I'm summarizing here, and we can come back to this, but it does vary a little bit across the different trials, but generally sort of 18 to 75 years old, had a major depressive episode, and basically had some measure of symptom severity at screening and at baseline. And this is just to segue a little to the EHR context. One of the challenges in bringing in the EHR is that in these trials, the main key covariate and outcome are these sort of symptom rating scales. So this MADRS, there's another one, PANS, that's used in some. And like these trials are looking at, like, is there a change in sort of symptom scores from baseline to follow-up, and is it different across the arms? And it's a relatively short time period, like 12, 16 weeks. In the EHR data, physicians are not doing these measures sort of regularly. We don't have these in the EHR data. Occasionally, like Duke, they do some what's called the PHQ-2, which is literally 2 items. That's basically how are you feeling. And so we like have this problem where the outcomes are just completely different. So in the trials, we have like these symptom scores. In the EHR, the outcomes that we have are things more like psychiatric admissions or emergency department admissions. So anyway, I'll come back to that, but that's one of the challenges that we sort of anticipated, but it's an even bigger challenge than we expected once we kind of got into the data. So for now, that's partly why I'm going to talk mostly about combining the trials.
Sorry, all 4 trials have the same arms?
Yes.
The 2 arms are the same, no?
Yes, I mean, there are some dosage differences, which we will ignore right now, but pretty much the same arms, yeah. Luke, yeah.
Why were multiple trials that were testing the same comparisons run? Or who are the agencies that would do that?
The pharmaceutical companies these are all like pharma run and funded trials. It's a good question, like why? So sometimes and this could be a whole nother conversation, they might be in different locations. So sometimes they're even different countries. They might have slightly different inclusion criteria. I think this is pretty common in the drug development process. Maybe some in the room know more than I do even, where like they don't necessarily do like one big study. They might do a series of smaller studies. But I don't think it raises an interesting question because I don't think they typically then do anything sophisticated to combine them for regulatory purposes. Like I think they just get submitted separately. Which
like different
regulatory agencies would have slightly different requirements, like European, Japanese, FDA. So you may actually need to run different trials.
And FDA requires 2 for new drugs. You have to have 2 separate trials for most of them.
Okay, thank you.
great. See,
And
I
also
told you
sometimes
people-
for different doses.
Yeah, slightly different doses or, yep. And sometimes they might, I don't think that's true here, although it might be. There might even be other arms, so they might be doing a 4-arm trial for some of them. And so here we're focusing just on these 2, but there might be some where they're even including another medication to learn about that. See, I told you, people in the room know more than me. So this is just a little bit of information on sort of who's in these trials, and it's true I'm hiding, and not purposefully, but just they are done in different countries to this point. So, but age 40s, mid-40s, 2/3 or so women across all the trials. Like broadly, the trial participants are sort of similar, although you'll, where is it? Weight, you can see a couple of them are smaller, and there actually is some geographic differences, like the trials that have the higher weight groups are more in the US versus Europe or Japan. But we're going to sort of argue that these are, for this purpose, we're trying to just pool them for to learn. You can see like the anxiety difference and where one of the trials especially, and a lot like that trial, essentially a lot of the time, and this is a different problem, trials might exclude people with certain, substance use or co-occurring conditions. So that's partly what's happening. Okay, so now I'm gonna just pivot to a little bit on the methods. And again, partly what prompted this was as we started working on this project, we were like, holy cow, there have been all these new methods that come out. Let's just like see, like, let's make sense of what's already come out instead of us like coming up with method number 36. Let's sort of try to organize the ones that are there and kind of learn about that. So a little bit of more formal notation. We'll have A to denote treatment status. We have some continuous covariates, although they don't always have to be continuous. Y for now will be a continuous outcome. S, study indicator, and then propensity score, but we can ignore that for now because we don't need it here. And so the estimand of interest is this CATE, so the conditional average treatment effect, which if any of you are in this world, it's a fairly common estimand. So essentially a difference in potential outcomes conditional on the covariates. And here you'll see also conditional on study. And in the little reading group before this, we were talking about this. That's actually not at all satisfying to me, because in reality, we want to be sort of learning about like future patients or kind of future populations. Most of the existing research, though, implicitly or explicitly estimates study-specific conditional average treatment effects, which again is a little bit weird because in some ways, like that's not super helpful to know, like in this study, the effect is whatever. Like we sort of have to believe that there's some unifying, underlying treatment effect estimate, but a lot of the time, most of the methods are actually conditioning on study, basically. Yeah.
I assume you're interested in like who are experiencing the, say, positive knowledge effects versus negative effects. So it's not like you're trying to estimate like for every X what the average treatment effect is more. Is that right? Or
yeah, actually, I would love to talk to you about this later because I heard this yesterday or maybe today that you're working on stuff about just sort of identifying.
Yeah, identifying like a.
So here we're just estimating the conditional average treatment effect. We're not trying to say whose is positive or negative.
Okay.
Yeah.
But if the X is like high dimensional, there are lots of different people, right?
Yes.
Okay.
Totally. So this is why I would love to talk to you after and
Yeah.
like think about how to sort of extend that for that. And I'll sort of come back to this because this is my crisis of. But people are doing this all the time.
Right.
And this is my crisis of like, well, what does it mean? Sort of standard assumptions in a room of statisticians have to at least, so kind of SUTVA, unconfoundedness of each trial, which we can assume here. Funny, okay. Maybe I have to, no, I just moved it, anyway.
It's unlikely to happen again.
It's sorry?
If you plug the computer into the power supply,
I don't have a power supply.
okay, then you
Well-
put up with it disappearing every now and again.
That's all right. It's only for a couple of seconds. So the trials are actual trials. That's fine here. Consistency, the outcomes we see are the potential outcomes. The fourth one is fine actually in the trials because that's just saying that everyone has a positive probability of getting duloxetine or vortioxetine in each trial. The final one is sort of the strongest in this context. It can be sort of relaxed, but basically that everyone in the population or every covariate profile in the population has a positive probability of being in each study. So we're sort of, most of the methods assume that you have kind of this full overlap. Again, some of the methods, you could have like some trials that miss part of the population, but then you need others that capture it. And again, so partly what we were trying to do, and this was Carly's first dissertation paper, it's coming out or is out in statistical science, is sort of just trying to make sense of all of this huge literature that has grown up in the past couple of years. And people like Kosuke are developing new methods still, and so it is quickly out of date. But we were sort of trying to just organize things. So what we're going to talk about are single study methods, so the methods to use in each study to model this CATE function, and then aggregation methods to combine across studies. The single study methods are going to be these three, and again, remember here, we're sort of in the machine learning world for today's purposes. Let me actually go just to this slide. So basically, and I think it was actually at a session, at a thing Giovanni and I were at last year where I learned, but now I'm forgetting what it was, like what S and X like mean. But so essentially, the S learner and X learner have fit models of the potential outcomes under treatment and under control as a function of covariates and treatment status. So the S learner does that through a joint model. The X learner does two separate models. So in a parametric world, you can think of the X learner as sort of the generalization with all possible interaction terms between treatment and covariates. In the machine learning world, it's just a little bit different, but that's sort of big picture what's happening. And then probably, if any of you, again, very popular approach now, the third approach that we'll look at is this causal forest by Weger and Ethy, which is, it's using a machine learning approach, but it's targeting the effect heterogeneity. So the S learner and X learner are both sort of discovering heterogeneity just through the models. Sort of, they just model the outcomes and then sort of see what pops out in terms of heterogeneity. Causal forest is doing the tree splitting in this sort of random forest-ish approach based on splitting on sort of effect heterogeneity. So it's a little bit more targeted for actually identifying effect heterogeneity. Okay, aggregation method. So so think about doing each of those in each study, and then we want to combine somehow across studies. So just as a default comparison, we'll think about complete pooling, where we just throw all the data together and ignore the fact that it comes from multiple studies, which happens sometimes. The next one is like the easy kind of like, if you weren't really thinking too hard, but like maybe it works okay, is essentially pool all the data together, but at least have an indicator for which study someone was in. And then we'll extend what's known as a federated learning method. So federated learning, again, I don't know if people are familiar with these, but federated learning is usually used in contexts where the individual data can't be shared. And so there's all of these approaches for figuring out how to minimally share information, like summary information, again, when you can't share the individual data itself. So what federated learning, it's a little hard to explain, and this was based on this paper by Tan et al., is essentially what you do is you fit a Kate model in each study. You then use that model to generate predicted Kates for each person in each study. So we'll have like, if we have 4 studies, 500 people each person will have 4 predicted Kates. We share those. So those are what gets shared to a central repository. And then we fit like a tree or forest or lasso model on those. So it's a little bit weird because you end up like, again, you have like 2,000 people, 4 Kates. So we have like 8,000 Kates, which we model then as a function of the covariates. But it's a way to do this, again, also in this federated learning context where you're not sharing the individual covariate data. Make sense?
Question. Your federated learning approach, so your model from different subsets didn't actually interact. Usually there are 2 steps. One is localized, but also there is a more important one is that, for example, the model in a local 1, 2, 3 should be interact and combined to perform better usually.
That's sort of the combining is the bottom step. So it's like we do them each separately and then we combine and fit another model
Yeah,
to
but
look.
you're looking for prediction somehow, like you, like for each model you have K models and applied for each individual. So you have K times N. But actually the model between like pairwise or like the models between them, like they didn't kind of interact.
Right, like you don't right, the way this is implemented, like your model 2 and model 4 don't learn from each other. Is that what you're sort of
Yeah, they
saying?
should interact if it's talking about federated. Otherwise, it's just like you split into K, right?
But
in another scenario for federated learning is that like it's like for privacy somehow like that. So you have to kind of learn in localized without sharing data, but you can share the model weights, for example. So you're still sharing.
that's sort of what we're doing here, except instead of sharing model weights, we share the models and then also share these predicted Kates across them all. But we're not sharing the individual like covariates.
Yeah.
Maybe there's a way to
Like
improve this,
stacking.
which would be great. The bottom step things get stacked. So yeah, we have like 8,000 Kate estimates, 4 for each of the 2,000 people. We can talk more, especially if there's a way to like refine this.
Wait, can you go back?
Yeah.
So the federated model, so the stacking piece is you're then going to fit a new model on all of the predictions which is the way of unifying discrepancies across the model.
Yeah, so the idea is sort of a like, we want one Kate model in the end. And so it's sort of, you see like, oh, does age predict all of the Kate estimates? I'm sure it could be improved. But yeah, that's sort of the idea. Did you have a question too?
I was just wondering, what happens if the different studies have different covariates available?
Oh, I love that question. And this is actually a theme of my meetings today, is people are like, what are the directions for causal inference? Like that is exactly one of the things. Is so like all of these research methods, like this, a few exceptions have sort of started probing this, but the standard approaches assume this nice rectangular data set with the same covariates, the same outcomes, et cetera. And scenarios where there's different covariates available, or as I was saying, different outcomes available, I think that's totally where a lot of work needs to still happen. There's been a little bit, like my colleague Nilanjan Chatterjee has done a little bit, and some others have done a little on that, but not much. So for now, we're just assuming this nice, clean matrix. Okay, we're also going to compare it with just like parametric meta-analysis, like fit a model basically that allows study random effects and kind of study random intercepts, slopes, et cetera. And we can pool all the data together and fit a big, sort of think of it as like a multi-level parametric model. Okay, I'm just gonna quickly, because simulations are never super exciting actually, so I'm gonna super quickly just present big picture and then talk about the application, which again is partly my like therapy about like what is the point in all of this. Okay, so typical, we set up a simulation with sort of motivated by our case study. We had 10 trials here, although that doesn't really, interestingly, it doesn't really change anything. 500 people per trial. And we kind of considered a few different scenarios for how much heterogeneity there is across studies. And we also varied how simple the true Kate model is. Again, I'm not going to get into all the weeds. You can look at the paper for all the details. So this is just the quick summary. And I want to point out a few things. So the colors are these different single study approaches, kind of what we do in each study. And then the kind of columns are how we combine across studies. So one point is that the circles in general are pretty close to each other, i.e. like what we do in each study doesn't matter a huge amount in terms of mean square error. And this is just averaging across all the simulation scenarios, which is important for the meta-analysis. So that purple meta-analysis dot like looks pretty good here, but that's basically because if the model is correctly specified, it works great. And if it's not correctly specified, it works horribly. So in reality, there's like the average is out, but really the meta-analysis is not a great approach. Interesting, the complete pooling, not surprisingly, is a bad idea, just pooling and ignoring the fact that, but again, people still do this. What was interesting to me is that the trial indicator across a whole bunch of scenarios, the trial indicator like was a reasonable approach, like a sort of nice and easy and, you know, just sort of essentially, and I think especially in this machine learning case where it can pick up interactions and things fairly easily, it gives it, I think, a reasonable amount of flexibility. And what's nice about that is, again, it's like very easy for people to do. Luke, you had a question?
I was just curious why complete pooling failed in this particular context, because it seems like if you have studies that are all the same size, then averaging them.
It's because the true Kate models differed across the studies, in at least for enough of the settings.
So what are you trying to estimate then if each study has a Kate model?
Yes. Oh, thank you. Thank you. I didn't specify. Right. This gets to our earlier conversation. Here, what we were estimating was essentially averaged across all of the people. So sort of for a person, how well did it estimate their Kate? And so kind of conditional on study. So, and then sort of across all the studies.
So the other methods were actually giving different predictions for different studies.
Yes. Yes, exactly. And then we're kind of testing it compared to someone's true effect in their study. Yeah.
Like on the trial indicator, if you build a model, how can you apply it to a new patient outside any trial? Like, do you match them by characteristics or?
This is Carly's third dissertation paper. This is what bothers me, is like, so, and this is what we talked about a little bit before now, right, almost all of these methods that exist are implicitly estimating this conditional average, like this study specific. And it's, again, it's not always super explicit in papers, but almost all the time they're doing that. But then in reality, we want to use these models to predict for future people who are not in a study. And so Carly's third paper, which I might allude to a tiny bit, is basically kind of exploring this idea of predicting for someone new and essentially integrating over the study distributions. But how you do that, I think, is, we could, you know, there's question about how to do that well.
Can I ask you
Yeah.
about the graph you showed in applications? Those dots, can they be estimated reliably, or
No,
do you
no,
need
this
the
is like,
luxury of a simulation?
you have to, this is only for simulate, like you have to know the truth to get this picture. And yeah, it's unlike a prediction, like in causal inference, like it's not a prediction problem because we don't know the true Kates in the real world. So this is just to inform, like we wouldn't be able to use this in practice to help. Yeah.
Can I clarify? So the fact that there were slightly different models within a trial between the covariates and the outcome, was it primarily due to just slight different in populations, or like how would that be? Like technically, the relationship between the covariates and the outcomes, right, should be like ideally the same. So why would
we were basically allowing some random effects that sort of, yes, maybe there's like, maybe the relationship between age and treatment effects is on average 0.5. Mm-hmm. But like in one study, it might be 0.4 and another in 0.6. And that could be because of just differences in the populations. It could be due to differences in the studies, like in sort of how they implement the intervention. Like, I think this is sort of what gets at, like, in a lot of traditional meta-analysis, there's sort of a like, and I think actually this is a good point, because maybe people don't worry too much about this, estimating this tau sub s, because they sort of have this belief that it's just constant across everyone. I don't think that's always going to be true, though. And so, but yeah, I mean, if you really think that there's just a universal truth, then any variation from that is just random noise. But I think that in some contexts, you might think that it's not just random noise, and it might be like there's actually true like variability, and again, like how the study's implemented, or how the treatments are given, or the exact dosage and things like that, or the populations, like Japan versus the U.S., things like that. Because also, actually, sorry, one more quick thing, and I see two hands. Like we also only have the covariates that we have the covariates for, so it could be that there's actually also some unobserved things that are really driving this, and that's correlated with the X's we have, that kind of thing.
That was my question.
Yeah. Yeah, no, and so it's like really just how well can we model?
Yeah. So if you believe that there's no unobserved things, then that's not a crazy assumption that S doesn't matter.
That might be right. I mean, you'd hope. And
well,
for science.
Wouldn't that be true unless there's something unmeasured that forces these to be different?
Oh, true. Especially if you think of like the study characteristics as the thing that's
that's what I mean. So there must be something that's unmeasured. So that's why you're worried about it, and you want to make sure that you're sort of adjusting for that unmeasuredness.
Yeah.
Okay. Thank you.
Yeah, and then.
I had a question. It does seem unrealistic to like believe there's some not study specific conditional average treatment effect, and yet, and maybe this is something you'll speak to. And like, why does this matter? Like, it seems like that is what people are after, right? Like an idea like, okay, if you're older than a certain age, we're going to make this rule of like, it's probably more likely to give this drug than that.
Yeah.
So it seems like that is the kind of what people are actually looking to use in practice, especially at these like regulatory institutions.
I agree. I think like that's the premise. Whether that is a reasonable premise or not, I think is an open question. And that's why one of the things actually we haven't really done, maybe someone in this room could do, but one thing we've been thinking about is, are there ways to display or sort of characterize the variability across studies to help people understand maybe when is it just like that's an untenable assumption. Because if the relationship between age and treatment effects varies tremendously across studies, that might be a sign that we shouldn't be using age to decide treatments. But I don't think people are doing that yet. Laura?
This was basically my question too, and I guess as I thought about it more, I thought in addition to thinking of it as standing in for all the unmeasured stuff, you could also think of it as solving the dimension problem, which is if you only have 4 trials and they vary on a bunch of characteristics, you can't actually tell the difference between actual trial-specific heterogeneity and just you can't sort out all the things that might differ between them.
Yeah, this is a super helpful conversation because we had sort of left this behind, or just, dissertations go, but kind of it would be good for someone to come back to this, like how do we measure the amount of heterogeneity cross studies in a way that then you could use that to help decide when sort of it makes sense to combine or not. Let me, I know we have a discussant, so let me sort of show my other, let me just quickly show you the data example and then some of my other. So this is one of the things where I'm like, what are we even doing here? The other, so I'll just show you quickly the data example, which is the other reason I'm like, what are we even doing here? And maybe Peter Cherchet is right, actually. But so in this case, I'm just going to show you the causal forest approach with the just trial indicator approach. So this is and Kosuke, this gets partly to your point earlier. And I wanted to highlight a couple things here. So this is just across the 2,000 people. Here is the distribution of their predicted conditional average treatment effects. Really, you should think about these as each of the 2,000. It's really like a patient profile, because the Kate is a function. It's not a individual predicted effect. It's a little bit of a subtlety, but anyway. And I want to highlight 2 things. So this is just sorted from low to high. The black point is the point estimate. And so you can see it ranges from -9 to +9. But huge confidence intervals, essentially a whole lot of noise. But often, most of the time, those confidence intervals aren't shown. Often people do this kind of thing and they'll just show the black line without the uncertainty around it. So then you think, okay, well, this isn't super helpful, but maybe we want to understand what drives the -9 versus the 9. So sometimes there's this thing called an interpretation tree where people basically just fit a causal, a cart to those Kate estimates just as a way to summarize. And so here you can see age is the first thing that pops up, weight, and then this baseline symptom score. So, okay, age maybe is the most important. So then maybe we could do something like this, where we plot the conditional average treatment effects by age. The red lines is because one of the studies, sort of to the point earlier, one of the studies only had age in bands. And so we just gave them the middle. So, okay, we can squint and be like, all right, maybe there's a relationship between age and the Kate, slightly larger effects for older people. But we don't have those uncertainty bands here in this picture. We could do that in a bivariate way and sort of see, okay, by age and BMI, do we see signals? But this is one of my, I'm like, if part of the problem here is for treatment decision-making and stuff, this is not really helpful, just seeing the distribution. This tree might not be helpful, but if in reality, we kind of want to summarize the effect heterogeneity based on a small number of covariates, why don't we just go back and start and just do a subgroup analysis by age? And so I've actually started thinking of these approaches, these machine learning approaches, more as an exploratory tool to develop hypotheses and then maybe go back and say, okay, let's now dig into this age and see if age is really driving it. Because it's just, but it struggled. So I'm like, well, if we knew that age, why did we go through this whole rigmarole?
You do have one result, which is heteroscedasticity, right?
Possibly, yeah.
And the uncertainty is sort of there. You can see it.
Yeah, that's fair. Yeah,
So.
Yeah, that's true. like older, yeah, we could try to characterize that a little
lot of
more.
the older people
Yeah.
have smaller variances, and
Yeah.
the real young people have much bigger variances.
Yep. Yep. Yeah, that's true.
Sounds like you should write a completely different paper.
Okay, let me just wrap up in a couple minutes. And again, so this is where like we can do all this fancy math, and like there is like all these methods being proposed, but like what does this mean in practice? So how do we interpret these results and findings if we really want them to be used in practice? And maybe we'll hear about this from the discussant. Like, how do we present this? Well, I mean, also, is there any heterogeneity? Like, this is not the only data we've run stuff on, and it is true that even like, at least in mental health research, it is hard to find things that feel like true moderators. It's just incredibly hard to predict treatment effects. So this is, yeah, actually, we've already covered most of these. Yeah, actually, we've already covered all these. So I want to, again, and then just come quickly back to the EHR data, because you're like, you told us you were going to talk about combining trials in EHR. But again, here we are just really struggling more so than we expected by the differences in measurement. That sort of yes, age is something that we do have reliably measured in both places, but these symptom scores we don't have in the EHR. Even like BMI and stuff is not great. So we are sort of in like a year, you could have someone from my group come back. We're trying to develop some methods to see, is there any hope of combining when we have different outcomes? Like, how do we kind of talk to some of you about that? But it's actually not clear you really get much benefit at all when you have different outcomes measured, because you have to make other assumptions. So it's messy, and it's also been another exercise in like, it's really easy to talk about using EHR data and combining stuff, but I've given this anecdote to a few people today. Like, we're using Duke and Hopkins EHR, and it was annoying at the time because both of the research funders were like, you need to use more than one EHR system here. You can't just use one. Luckily, both grants got funded, so we had money to do both. And it's actually been a really good, like, probably we should write up a paper about like the differences in these systems, and that sort of like Duke has a totally different way of coding emergency department visits and inpatient admissions. Hopkins does it differently. Duke, weirdly, like we had this crazy high rates of fibromyalgia in the data that we had to like dig into. Like, it is messy. And sort of like, you really just sort of like, it's like another just case example, and like, it's easy to be like, oh yeah, we can just use this data. But in practice, there's this stuff. And to Picori's credit, they pushed us to really have like clinicians and things on the team. And it has been crucial because like we can talk to them and be like, how do you code this in practice? And really having that on the ground knowledge about what is behind the data is crucial. So it's been really a lesson in that. Okay, I think that I don't need to summarize all this. I'll just leave. So that's kind of where we are, is like, yay, these fancy methods exist, but kind of grappling with what does that mean in practice. Maybe our discussant will have all the answers. And I think the goals are really great. And so the question will be, how can we sort of use them best to learn to improve this sort of decision making? Anyway, so here are some of the references, including the two. Carly got married, so she switched from being Carly Brantner to Lupton Brantner. Or actually, sorry, no, I just screwed that up. She used to be, she got married, she changed her name, it used to be Lupton Smith, now it's Lupton Brantner. So you might see different names for her. But those are the two papers. The fourth and fifth bullets are the ones sort of based on, that the talk was based on. So I'll stop there and let our discussant come up. Thank you.
Liz is just, I just wanted to say that has such a wonderful track record. You could pick up almost any of her papers and get some deep thinking and usually some explaining and synthesizing of the field. And so I just wanted to give a shout out to a really wonderful researcher that I admire. And you should also take any chance to talk with her, because it's usually an interesting conversation, as this talk has provided. So thank you for making the trip and coming up. Also, in the course of this, you might have realized that you sort of walked in halfway through a conversation with all these references to the reading group. Well, that doesn't have to happen to you if you go to the reading group. So keep an eye out for the references to those invitations, because that's really just a really wonderful way to have like a pregame your stat colloquium, like if you really want to play in the major leagues or something like that. Next, Ibrahim is head of machine learning for a clinical outcomes lab and instructor in radiation oncology. He's located in Mass General, which is part of Harvard, yes, and works on machine learning and heterogeneous treatment effects. So seems like a pretty good discussant for what we've been talking about. So I'm excited to hear what he has to say. I also was noticing that he has a background in mechanical engineering, which means he probably understands deeper than we do on how the world works, which I'm also excited about. So anyway, so please give our discussant a warm welcome.
It's a real pleasure and honor actually to be here, and also honor to me to be discussing your presentation. I don't know if I'm qualified enough, but I'll do my best. Thanks, Luke, for the kind introduction. Dr. Schwartz, addressed a really important topic in medicine, something that we see all the time in the clinic. I work in cancer research, and in cancer, this is something that I don't know any disease side that we don't see that effect, where we look at expected outcome out of clinical trial, and then we say, okay, the average survival after a treatment is 12 months, for example, for liver cancer. And this is the overall distribution. This is what we understand what's going to happen after diagnosis. And if you measure it using the average treatment effect, this is what you see. But in reality, what happens is that some of the patients will just live 3 months and others will just live much longer. They're just lucky. They respond better to the treatment. And for that, here where treatment effect heterogeneity is very important, because it will allow us to identify which patient belong to which subgroup. And here we want to measure something like Kate. So personalized medicine is actually about trying to identify patients at risk and tailor treatments to them. But in order to measure this, as you mentioned before, we need at least 4 times the sample size that we need for measuring the average treatment effect. Clinical data are pretty tricky and very hard to obtain. Patient privacy between institutions is very huge. Sometimes it takes years to just develop a data sharing agreement between institutions. We have a lot of them pending and we're not able to touch the data. A lot of them are just like clinical trials are powered for measuring average treatment effect, but they're also very expensive to run. They focus on the average treatment effect. We typically don't have enough number of patients. Going back to registry data, they're confounded even by preferences of the doctor or by so many other environmental factors that affect the treatment effect. So Dr. Schwartz is pioneering a leading approach in order to overcome these challenges by combining data from different clinical trials, and also hopefully we're gonna resolve the problem of observational studies. So she's a PI on major grants on this topic and published leading papers on that topic. So with your efforts, we'll be hopefully able to benefit from the powered sample size for observational studies and the unbiased data set and randomized clinical trials to overcome this challenge. So you've developed a lot of parametric and non-parametric approaches for estimators and for integrating data through. Okay. All right. Integrating data through through aggregation methods, and all of this has strong potential to move forward towards personalized medicine, and to try to be able to to stratify patients into the right risky groups and select treatments for them. So single data set are before all of these efforts, single data set typically relies on single models, sometimes combine multiple models with the evolution of ensemble modeling later on. But with data integration, we can enrich and diversify our data sources. We can also have power, more power to detect effect moderators. And in my opinion, we can also have a better opportunity to understand hidden confounders by discovering different patterns across different institutions or trials. So if I want to start with something is talking about S learner versus X learner. And in the clinic, I believe there's so just to recap, S learner is a model that takes both confounding factor, like both patient-specific factors, X, and the treatment, A, and make a prediction out of it. However, in X learner, we split into two models where A is not an input to the model, where we have model for treatment 0 and model for separate model for treatment 1, and then we have two models to make predictions. As learner, I've seen practically as learner is kind of easier to implement for personalized treatment selection because it's just like one entity where decision makers can use and try different treatments and then select which therapy will work better for patient. Here I'm showing just an example from radiotherapy. There's mainly two different versions of delivering radiotherapy, proton therapy and photon therapy. And on the x-axis is the dose, the y-axis is the volume of the tumor or the organ that we're concerned at. And there's difference in dose distribution. So the first thing that came to mind is, if we do as learner and we combine two different treatments into one model, are we diversifying better the training of these models? Are we providing better training? Maybe yes, but maybe that will also require that the model is more extended and more deep. So in addition to having one model that helps decision making, are we having more diversified data with S learners? And because we're combining two cohorts, are we having more patients to train the data on? So eventually, would S learner be more powerful overall? The data showed that sometimes S learner outperform X learners, but X learners and other factors, like when we look at, for example, pooling. So when we pool by trial indicator and complete pooling, the S learner was more powerful than X learner, slight marginally, but still more powerful. But then the X learner outperformed the S learner when there's ensemble modeling, and probably that source from some hidden confounder that the trials, even the control trials, have, because putting data from different trials all together in one entity like S learner clearly didn't lead to a better performance than the X learner. So probably X learner is kind of correcting for that hidden confounder. I do think X learner has potential application. What if we have comparative trials, for example, trying treatment A versus treatment B in trial 1 and trial 2, comparing treatment A versus treatment C? Is this an opportunity to better understand the effect of treatment A on outcome disparity? And can we combine these two? So here where X learner could probably be a better performer or a strong application for having two models and then assembling them in a way that we can understand the heterogeneous effect of treatment A and extracting information from multiple data sets. In terms of aggregation methods, we've talked a little bit about federated learning. So where essentially the purpose is, how can we use patient data from different institutions while still protecting patient privacy? Because this is one of the most limiting factors in sharing data, which is also important. And the idea is, if you have a centralized model and instead of sharing data from different institutions to the model to train the model, why don't I share the model weights to the institutions, let them train at the host institutions, and then centralize the weights? And then what I've seen in your paper is an extension to that modality, where a 3-step process would start by going to the single trial, developing a CATE for it, and then applying every CATE to every single individual across all the trials. And then we have an extended data set, and then taking all the predictions to assemble them into a centralized model. And I think this is a very powerful approach, in my opinion. It allows us to, it will have a lot of implications on federated learning and the extension of federated learning is it will enrich because this cross trial training may have the potential to uncover hidden effect moderators that we wouldn't be able to do without by relying only on a single model.
Can I ask a clarifying question on that? So in this federated learning model, where do the patients, for the final predictions, you need patients that are not private anymore? Or do you have like a collection of patients that are sort of like public or profiles that are public? How do you resolve that piece?
So that will be outside the training. So the federated will be just during the training, and then the model will be just logged and applied to locally. So then the model after the centralized model is finished training, you can just send it.
Can you go back a slide for a second?
Yeah, sure.
And Luke, another way to think that what gets combined are just the Kate predictions. And so those are less sensitive because it's not like, it is individual patient data, but it's like just the Kate prediction for each person. And so the sharing of that is okay.
But how do you get the Kate predictions for a single person from all three sites?
You send the Kate model to each site. So you say, here's our random forest model. Like you sort of send, like in a parametric way, you'd be like, here's our coefficients.
So it's like patient ID prediction.
Yeah.
Is what you share.
Okay.
Yeah.
Or multiple predictions for every patient, and then you send back the predictions.
Yeah.
Yeah.
Okay. Thank you.
I also have a question though about that. So does the Kate come attached with a vector of the actual covariates from each person?
No. Oh wait, sorry. Yes.
I was going to say, don't the X's have to come back with the Kate? Otherwise, how do you do discovery on like
because
what
then you need the
determines
model.
the Kates?
Oh my gosh, why? Because that third step.
Or do you get like? Yeah, that was the part I didn't understand. Do the X's have to come with the Kates?
Yes, because in that third step we model the Kates again as a function of the X's. Yeah, so then they're sharing.
If they're sharing X's, I guess I still don't understand how it's still privacy preserving.
Sorry, all right, apologies. Speaking of Luke, like running from one thing to another. This is like inspired by federated learning because this sort of approach is used in federated learning, but in this context, the data ends up being shared. Sorry. So yes, in a true federated, like the approach of like step 1, step 2, step 3 is sort of inspired by federated learning. But you're right, in this case, we actually do share. We have to share the X's.
But an alternative implementation is the one that he was alluding to, where you federate the case studies, and then you have your own data where you do the stacking.
Yeah, if you have, right. Yeah, true.
Oh, like Central has their own set of
profiles. Yeah, like we do it just for RCT1 or something, like, yes.
It's a different architecture.
Yep.
Let's share it.
It's worth just adding one more fact, which is if you federate the predictions or the aggregates, that's not actually privacy protective. You have to add one more layer of like differential privacy, and then you're good. It seems privacy protective, but it's actually not.
If you only have the prediction?
If you have to, in the hospital, which you probably do, guarantee the privacy of everybody, it's not privacy protection.
I'm not sure this world is thinking about that.
It is not privacy protective. You have to add a differential privacy layer.
But you're saying the fit Kate function would
If you add a prediction, if you're going to, I mean, the simple version of this is we're not going to make the individual level data available. We're only going to make a prediction for you from my model. Okay. Well, there are conditions under which that will reveal everything about you.
You go and if it's a tree, you go find that prediction.
Yeah, exactly. In fact, the better the random forest model, the more likely it is. Right? And if you want to actually guarantee that nobody's information is revealed, which is, I think he's legally required to do this, not us. Then you have to add a random component at the end, which is differential privacy.
So typically, we cannot go back from the prediction to the covariate because it's just so complex. Like if you're using machine learning models, the correlation is not indicated. Like it's kind of a black box, and the patient properties or like the important information that, like We can go back to blood counts.
The computer scientists have utterly ruined our day. Okay, I mean, if the story is that you have to protect everybody, then there are exceptions to that rule, right? You add one more person who has extreme values, and you know what the effective outliers, right? You know, there are exceptions to every one of those things. Sure, like my view, I'm sharing data sets all the time exactly like this. My view is, yeah, but it's really hard. But if the rule is you have to protect everybody, not just 90% or with very high probability, then this is not privacy protective, right? But another layer of you add very specifically tuned random numbers to this, which is called differential privacy.
Yeah.
Will protect it, and you'll still be, and with statistical corrections, because you're adding random error, you can make inferences with slightly larger confidence intervals and everything's okay. So just to make things a little harder for you.
But do you actually need real combinations of X's, or do you just need a sufficiently rich set of combinations of X's on which you have fit your Kate models? You can share those. Yeah. It could be totally synthetic unless you need the distribution of the X's to be the correct ones from the trials. But I'm not sure whether you do here, because it's all conditioned on X, and you're going to try and make predictions for some hypothetical future distribution of X's. So I think you just need like a large collection population, of X's, right?
Yes. Yeah. Yeah, that would actually be an easier way to. But I'd be curious afterwards if anyone is more in the federated learning world. I don't think they're thinking about this differential privacy issue.
There is federated learning with differential privacy. So is it?
Okay, good.
Yeah, it's
but
all
I think
doable.
some of it, yeah. But I think a lot is.
You're doing the hard stuff. They would think of their stuff as the hard stuff, but you might have to talk to them.
The way I understood it here is that you don't necessarily need the covariate of each patient, but you need to know which covariates to use, and you need the weight of these covariates coming from these institutions, and this is what you stack them with.
I think Laura's strategy is the right one, of just make a fake population of people. For this purpose, that works perfectly fine.
But what if one data set came and then we learned from it, and then another trial happens 5 years down the road, and here we're like a complementary method to federated learning, which is transfer learning, just learning the prior knowledge that was extracted before and applying it to a new data set. Right? An example of this, say we're measuring treatment A from 3 clinical trials, and then we create the Kate for A, and then a similar drug came out in the market like 5 years down the road, which is called B, and then we have 2 clinical trials. Do we need to start all over again, or can we borrow the existing knowledge from treatment A and just like adapt that into treatment B, and this could increase more like the power in the data. Do I still have time or? Okay. So I just want to say that your work inspired me to think a little bit on moving on how can we apply this to something that's related to my field, radiotherapy. And the motivation here is, we've seen before that the treatment is kind of encapsulated in 0 or 1, because in most of the cases it is like that, like drug A versus drug B, or this is how clinical trials are designed. And there's, especially in new targeted therapies, like radiopharmaceuticals or even external beam radiotherapy, we can measure exactly where the dose is going. It's not like systemic therapy where we just give that amount of drug and then watch what's gonna happen. And in that sense, the way it happens is that they take MRI images, they take CT scans actually before treatment, and then they can contour the tumor and they can contour other organs at risk, and then you can plan treatment, and then the treatment is actually different for every patient depending on their anatomy. So the treatment here is really hard to encapsulate in just one variable. It becomes a 3-dimensional information, and this will induce complexities, because whether the dose distribution is on the upper left, whether the tumor is in the upper left corner of the liver versus next to the different veins next to the stomach, is completely different outcome. So the question is, can we extend the framework to include that effect? Typically what we do in outcome prediction for that is that we employ neural networks, because neural networks can just abstract these three-dimensional information to one-dimensional information, and then we can integrate patient-specific properties and allow them to integrate. So this is just like a proposed kind of methodology if we can extend or move forward in order to integrate layer-wise transformations to capture interactions instead of multiplication. This could potentially allow us to harmonize combined data sets using different approaches. Really excited to discuss this with you. This is what I have for today, and I'm happy to answer questions or talk about any other, like about things related to this work. Thanks.
Here is the image. Is this the image patches or instead of like the EHR, right? The small patches.
Can you say again? Sorry.
There is a small patches, right? The boxes, like on the figures, but that's actually you are extracting image information, right? Instead of EHR, right?
Instead of
like electronic health records information, like text information. This is image information, right?
Yes.
Yeah. So actually, yeah, because I did something similar. I think those are very distinctive, but of course you can combine them. Yeah, let me get my point. Because this is more like this convolutional network or something.
Yes.
You blah blah learn features from the images. But actually, from the professor's thing is like electronic health records, which is gender, sex, and blah blah blah. It's text.
So these are X. These are like the image here is a treatment, not like we're not using anatomical images for the prediction. We're just using a treatment that is three-dimensional matrix instead of being one value.
Yeah.
But the
profiles. Those profiles.
Yes, those distributions.
Yeah. Yes.
Just to clarify, so and then the goal is to estimate. You would have patient characteristics, and then you'd have treatment represented by this three-dimensional image, and it would predict degree of success, like you would predict your outcome of applying that treatment to that patient.
Yeah, because now you can vary A, but instead of varying it between 0 and 1, you can change the dose distribution.
Oh, so you could potentially explore how you should dose a patient.
Redistributing the dose for that specific patient and avoiding clinical organs at risk depending on like an example of that is liver cancer, where in patients who had high albumin, which is a blood count that we can measure routinely in the clinic, irradiating the portal vein, which comes in the lower right corner of the patient, is critical because high albumin already indicates declined liver function, and irradiating the portal vein becomes induces the patient to liver toxicity and they die from the treatment. 25% of the patients do that. So this is what I mean. Just like trying to adapt A in a 3 dimensions, but for every individual patient depending on their X, and to see if there's any way to select those distributions.
Now we just open it up generally to questions for discussant or speaker. I'll come up here and glare at people as necessary. So we have a few minutes if there are things that people want to discuss. And hopefully this is an open-ended conversation. The goal of this seminar, again, is to start talking to each other across the university. So this discussion can basically be obliquely talking through our discussant and speaker to each other. That's totally fine. So, yeah.
Fantastic talk, both of you. My understanding, you kind of mentioned this, is that like the uncertainty around decay is always huge. Is it ever not so big as to be uninformative? This has been my kind of like worry or critique of like this line of research as opposed to the like subgroup analysis approach to effect modification, is that like it seems it's like a holy grail. And to ever think that we could have enough certainty requires so much smoothing and assumptions over distributions, though. I'm just curious if you think that like there is any, fruit in this research in terms of not even like the methods, but just like a confidence interval around a point estimate.
I would love to hear from anyone in the room. I have the same question. And I've like heard, I'd be curious, like I've sort of heard rumors of cancer treatments where there really is like clear heterogeneity, but there I also wonder, like, do you really need the whole Kate function to find that? Or is it really just like we have this gene. And if you have the gene, you do A, and if you don't have the gene, you do B. So I don't know, anyone in the room? Yeah.
Yeah, so my view is that I think you're right that if you are estimating, conditional average treatment effect for each of these different set of X, you just don't have enough power to detect anything. But the way, like I've been dealing with it, it's a different purpose, but you basically try to use the machine learning algorithm to estimate a subset of the patients who have, say, large positive effect. So you can sort them like you did.
Like sort of just find the
But then you look at the cumulative effect instead of like each data point. So you start like say top 10% or top 5%. Then you can start getting a much better confidence interval because just you have more pooling going on. But then the question is like, then how do you characterize those? Suppose you discover, top 10% are actually statistically significantly, benefiting from the treatment. But then it's coming from the black box, so you still want to interpret
who is in that 10%.
Who are these people? So.
I mean, the other question would be that maybe this is operationally the same as what you end up doing is like, we don't actually care maybe if the effect is 2 or 2.5 for someone. We just kind of need to know, is A better than B for someone? And so a different, maybe the Kate isn't actually what we want in any way. We just want to know, is there evidence of a positive versus a negative effect?
There's also I think it's Kennedy or Naus or something like that, talks about inference on, basically you take your Kate predictions and then you regress on a much simpler model and you get what they call GATE, group average treatment effects, which are essentially, you use this very poorly estimated Kate model, and then I think it's essentially what Kosuke is saying is you aggregate it down on a simpler covariate.
It's like a parametric version of the interpretation tree.
And exactly. And there's some work to show that the inference you get from that is valid, and I think the confidence intervals are smaller, so maybe there's hope.
So the one place I've seen these things work is in tech companies where they're running experiments on 10 million people. And there it's basically used actually for what you were saying, which is basically exploratory data analysis. You use it to figure out where you're getting weird effects. And then you go and you say, okay, is there something actually happening here? Do we need to design more personalization for those people? And it's basically, so basically every single tech company has this automatic checks after they do their A/B test to look for heterogeneous effects and basically does it in this way. But it's on 10 million people. And there you have power.
I think that's just cheating.
Some applications, it's not enough to have one variable to stratify the risk. To measure a function of an organ, you may need 5 or 6 blood counts, and here where it becomes hard to put them under one category because you can end up having different levels. I'm sorry, there was a question. I'm sorry.
No, not at all. I just love this idea that the Kate is the wrong target, and what you actually need is the conditionally best treatment choice. It's like the drug that, the choice of drug is the actual target for an individual person. Conditional on X, which drug should I give you? Is anybody doing that? That sounds so cool.
I mean, isn't this basically what multi-arm bandits are kind of trying to do during the trial? Contextual bandits, they look at your context and they try to give you the best possible treatment. I would think that's probably the best.
In the adaptive trial.
In an adaptive, not even in the trial. I mean, you can think about this. People who are trying to do this in healthcare where there's no randomization. The computer scientists are basically trying to say people come in, they have some covariates, and I want to give them the best possible treatment. There's no randomization. But as I'm seeing how they respond, I can sort of update my thing. So I think this is where the interface of reinforcement learning and bandits and causal inference is becoming really, really interesting because those methods are really, really connected. And I think that's kind of what you're describing here.
Or optimal policy learning, right? Is that another phrase for the same thing?
Which, again, is kind of the same thing with different terminology, but under the hood, it's the same thing.
I was just about saying, this sounds very similar to stock picking in the finance literature, where they do this using a similar method, but it's more like picking particular for portfolio management. And where there's much more data on availability.
Gary had his hand up and then Giovanni.
So we're all thinking of this from the patient's perspective because we hope one day to not have to be a patient. But the people that are underpowering these studies, right, the ones that we all advise, and when they finally figure out the ATE and they arrange the budget, it was exactly as you said, Liz, like they shoot for the ATE because they finally understand that, and then you say, would you like to look at subgroup effects, and they say, oh, yes, and you explain to them that they need to spend a lot more money, and then that just goes away. So from their perspective, this is probably the wrong way to look at it, right? Probably what they care about, particularly like a pharmaceutical company, they care about a completely different quantity of interest, which is, give me a large group of patients described in some way for which the effect is large. That's not the ATE, that's not subgroup effects, that's a completely different thing that we could go after.
Well, I might also argue that often trials are designed with that group enrolled. I mean, a lot of trials, they sort of have an idea of who is going to benefit. That's partly why a lot of mental health trials exclude people with co-occurring substance use disorder or, sort of other things. They try to get sort of a homogeneous selected population that is likely to show strong effects.
Sure, but on the basis of theory, which,
on the basis, exactly.
Which we know we don't actually have in this field, right? So, but doing it in the experiment,
if they did it in the experiment,
it may be adaptive or something, but it seems like that's really what they want.
I don't know if FDA would. Giovanni?
Yeah, I wanted to go back to your comment about the fact that many of the methods that you reviewed are looking at estimating the conditional on the study label. Mm-hmm. And maybe it's a two-part question. The second part would be conditional on the answer to the first. Do you think, are you suggesting that this is what people do in practice while there would be methods for doing a more generalizable estimation? Or are you suggesting that there are no methods for predicting the future, a patient from a future study?
I think there are methods. And I think this is, again, one of the nuances around, like, in this proliferation of methods, they just tend to not do this. But, I mean, you could imagine, I was talking to someone today about this, like, if I was trained in a very Bayesian parametric way, we could put a distribution of random effects around study, and then we can sort of think about like a superpopulation of studies, essentially, and then just sort of draw from that distribution to kind of predict for the future. Or, I mean, that's like the most obvious to me. I'd be curious if there's ideas. I mean, I guess theoretically, you could use, we could bring in ideas of meta-regression, and if we had characteristics of studies and enough studies, you could model the effects as a function of study characteristics to actually better do that. So I think there is hope. And part of my point was really just that it's often unstated sort of what really the goal is, or it's sort of this implicit belief that there's just this universal truth, like how meta-analysis, I think, for years has kind of just had this implicit statement.
I've seen several applications which companies that don't have incentives to provide the data. Do you think just the summaries from papers, what is public, can be useful for this type of inference?
No, I don't really. I mean, there's some work on subgroup meta-analysis with subgroups, but the problem is then without the individual patient data, it's sort of confounded with study. Basically, so it's really hard, and like you run into ecological bias and challenges like that. So short answer is I think without a lot of extra structure, it can't do much. The network meta-analysis, you had an example with like study 1 is A versus B and study 2 is B versus C or something. I mean, I guess theoretically you could start extending this to that world. It'd be a little more complicated.
Let's thank our speakers.